covering in this class is fluids, which is going to occupy us for most of this week. And so as you can see, I like this picture, even though it's kind of dorky, but fluids, both liquids and gases of all different types are fluids. And some of them, like water, are probably what you immediately think of when you hear the word fluid. But things like honey or helium or blood, maybe you're not immediately thinking about them, but hopefully it makes sense. They're all things that flow. This is the idea behind a fluid. It will naturally deform, and it doesn't really have a set shape. It just kind of fills its container. For liquids, that filling happens, due to gravity starting from the bottom. And for gases, they just kind of expand into whatever shape you give them. Now, I guess I'm going to mostly follow the book here. So these section numbers are from the book. And so that's for you all in case you want to, like, if you see a lecture slide and you're like, this is confusing, you can go back to the book and, have an opportunity to read some more about it. The textbook for this course is pretty good. Some of the ordering of stuff is weird, but there's a lot of detail, some good derivations. Anyways, but I'm going to also just mention random aside stuff that's maybe beyond the book or in addition to the book. So to start us off on that, plasma is also a fluid, and it's good for you to know that fact because plasma is actually the most common state of matter in the universe. So I'm an astrophysicist, so I really look at a lot of plasmas because the whole universe, the space in between galaxies, is actually a very dilute plasma. But plasmas behave differently from other fluids because they also have electric and magnetic forces involved. And so that's a topic for 3C. But anyways, so as you can see here, a gas will fill a box, and the gas molecules actually have enough freedom. The intermolecular forces are small enough that they can bounce around, go against gravity, whatever direction they'd like to go in. And you can pretty accurately imagine them as just little billiard balls that smack against each other occasionally, but mostly they just hit the walls of their containers. And so we'll talk some more about some of the properties that this leads to, but you can probably imagine, the most obvious one, which is pressure, that if you fill a balloon, for example, with gas, that it'll exert some pressure on the rubber of the balloon, and that'll be countered by the inward, springiness of the balloon itself. So for liquids, like I was mentioning, the molecules are much closer together. So you do have notable intermolecular forces for a liquid. And even though these bonds are weak enough that the fluid can flow, in a lot of situations, especially when we get to discussing more viscous fluids, these intermolecular bonds become really important. So you can imagine for something like honey, it can flow if you wait long enough, but those molecules are really stuck together in a pretty complex way, and that leads to this viscousness. Okay, so the first property that we're going to talk about is density. So density is represented with this kind of curly Greek P, which is the letter rho. And here we're talking about what's known as mass density. There's also number density, but for now we're talking about mass density, which is an amount of mass per some volume. So I know this is probably rather basic, but one of the most common mistakes people make in this first section of the class when thinking about density is unit conversion. So that's why there's this big cube on the left side here. So if you have a 1 cubic meter volume, then that will be 100 centimeters per side, but you have to cube that entire quantity. So you'll have 10 to the 6 cubic centimeters per cubic meter. And something that often trips people up is that 1 liter, which is a nice human-sized unit, right? It's like a large individual soda bottle is a liter. This is like, this is like 600 milliliters. so a slightly larger bottle is a liter, is 1,000 cubic centimeters. So there are 1,000 liters per cubic meter. And the thing people usually remember, most people, including myself, don't usually remember this directly, but you should remember that a milliliter is the same as a cubic centimeter. This is something that comes up in medicine a lot when you get into dosage of liquids. Somebody will say, like, give the patient this many cc's of whatever, cc standing for cubic centimeter. That's the same as a milliliter. And so 1,000 cc is 1 liter of fluid. Very handy conversion to know. And so anyways, those are the volume portions of things. And then the density is how much mass a substance has within some set amount of volume. So these values in the table are densities in kilograms per cubic meter. A good one to know, the only one that I really would recommend memorizing for this class, is water. And it's a really nice number for fresh water at around room temperature. It's 1,000 kilograms per cubic meter. And actually, I say room temperature, but it doesn't actually matter that much what the temperature or the pressure is. The density of water is pretty stable as long as it's composed of fresh water. You can see seawater is a little bit more dense, and that's because it has some heavier salts in it. And blood is even denser, but not by very much, right? They're all at the percent sort of level of difference. And then air is significantly less dense. So gases in general, significantly less dense than any liquid. And the most dense thing listed here that's a fluid, at least, is mercury. So mercury is by far one of the, if not the densest fluid, at least commonly available. Unfortunately, very toxic, or we would do lots of fun experiments with it in class. But you know, the cool thing about mercury specifically is that it's actually, so the human body is pretty close to the density of water, a little bit denser when you're talking about the solid material. But if you consider the fact that we store air in our lungs, the body as a whole can be a little bit less dense. So that's why you can float in water if you're, we'll talk more about floating momentarily, but you can float in water if you kind of keep some air in your lungs. But if you breathe it all out, generally you'll sink. In mercury, even if you exhale completely, you'll continue to float, and you'll actually float with barely any of your body below the surface. So it's like a really crazy experience. And people used to love to do it back in like the 1800s. Floating in a pool of mercury was like the height of fun. Unfortunately, it's a heavy metal, so it is very toxic and, you know, not great to float in. But anyways, so this is the idea of density, one of the most important fluid properties. Now, I should mention, for liquids, density is pretty constant. So for water, no matter what you do to it, the density is going to stay the same. But for gases, the density changes, right? So gases can be compressed. So if we compress some number of molecules of gas, now we have the same mass in a smaller volume. So we've increased the density. And you can imagine that we can keep increasing the density until eventually that gas condenses and becomes a liquid, and then it'll be incompressible for its liquid state. Okay. So now on to the next fluid property, which is pressure. So I've put some units here, but let's not get distracted by them quite yet. Pressure is this idea that a fluid pushes out when it's being pushed on somehow. So, you know, gases actually have a natural pressure to them, which is caused by the fact that the molecules are flying around, smacking into stuff. So a gas will have pressure even out in outer space. But a liquid will naturally, sort of in outer space, it'll naturally form little bubbles due to surface tension, but it won't have so much of a pressure. The pressure in liquids is due to the force of gravity. And so that's why you can see in this column on the left here that the water shoots out more horizontally. So with more velocity, the farther down in that column of water we go, because the pressure is higher there. So the higher the pressure, the more force coming out of a similarly sized opening, and the more velocity that that water has coming out of that opening. And so the definition of pressure is a force per area. And so the units of pressure are newtons per square meter. And the unit Newton per square meter has a name, which is the Pascal. So Pascal was one of these like 17th century physicists who did a lot of work with fluids and gases and things like that. And you'll see his name come up a few times as we go through some of this material. A Pascal is a pretty small unit of pressure though, because you can imagine a square meter for US people is 3 feet by 3 feet. So a pretty big area. And a Newton is the weight you would get. So remember, force is mass times acceleration. So a Newton is the weight you would get from 1/10 of a kilo. So 1/10 of a kilo is something pretty small, maybe phone-ish sized, spread out over 3 by 3 feet area. That's a Pascal. So a pretty small unit of pressure. An atmosphere, which we'll talk more about the atmosphere a little later, is many pascals, 100,000 pascals of pressure. So the weight of the ocean of air on top of you right now, every square meter has 100,000 newtons, or the weight of 10,000 kilograms. So kind of crazy, that value. And then due to the way that we measure pressure using barometers, which again we'll see shortly, we have some other unit of pressure, which is the millimeter of mercury, or you'll also see inches of mercury in the US. Millimeters of mercury have their own fun name, which is the torr, which is named after Torricelli, who was an Italian physicist that actually came up with the idea of atmospheric pressure and figured out this kind of crazy fact that we live under an ocean of air. And so you'll see torr and millimeters of mercury a lot if you work with any sort of pressure-based medical equipment, or if you're even, so in the US, blood pressure measurements are a little weird, but even with blood pressure and that sort of thing. And the idea is that by pushing on some mercury, you can make it move up a tube. And so the amount it moves up the tube, if you measure that distance in millimeters, that tells you something about the pressure. The higher up the tube the mercury moves, the more pressure is being exerted on it. And then in the US, we often use PSI, pounds per square inch. As you can see, it's another force over an area. And a good rough number to know to help orient yourself is that like a car tire or something like that. So a car tire is like 35-ish PSI, which is roughly like 200,000 pascals. So atmospheric pressure is roughly 15 PSI. So every square inch of your body has a 15-pound weight of air pushing against it. Kind of crazy. Okay, so like I mentioned, if we look in these upper two pictures, this is what would happen in a weightless environment. So the gas would just act like normal, doesn't really care. It's just molecules whizzing around, but the liquid would tend to bubble up, and we'll talk more about why it bubbles up and the strength of that probably tomorrow. But it's due to surface tension, this fact that liquids, because they have intermolecular forces, they want to stick together more so than gases do. But as soon as you take these two containers to a region with gravity, the weight of the liquid itself will pull it down and cause it to fill the bottom of the container and exert some pressure that increases the deeper below the surface you go, whereas gases will basically act the same way. So you can see it says that gases will have a slightly lower density on top and a slightly higher density on the bottom. If you want a number for this, if you have 100-meter tall tower, so 300 feet or so, so like more than a football field vertically, then the density at the top, row at the top, compared to the density at the bottom will be the same within 1%. So less than 1% difference for 100 meters. So it's a very small effect. Any normal laboratory apparatus, you can assume that the air will be of a constant density. Like this room, the air at the top is going to be the same density as the air at the ground. Very good assumption. And you can see we have a fun picture over here of what happens when you let water loose in a free fall sort of environment on a space station, which is that it bubbles up in this fun way. And the pressure inside that bubble is going to be very low, almost zero. So you can imagine, and many science fiction writers have, if you had a huge bubble of water in space that you could just swim in, it would be really weird. You could go to the middle of it and your ears wouldn't pop. You wouldn't notice any difference. It would just be like you were swimming at the surface. Now it would be, anyways, it would have a lot of weird physical properties, but let's not get into them. So talking about these sort of gas pressures is really important. So this picture on the right here is of the atmosphere on the Earth. And because the atmosphere is hundreds of kilometers tall, there actually is a noticeable difference in pressure as you go up higher and higher. And so you may have wondered as a child, why doesn't all the air just escape from the atmosphere? Well, some of it does, especially if you release helium into the atmosphere, it'll just leave the Earth. But in order to escape, these molecules have to have enough velocity to overcome the attractive force of gravity, which doesn't happen too often. The temperature of the air around Earth is low enough that the molecules are slow enough that they don't tend to leave. And so you end up with a buildup of pressure close to the surface of the Earth, and then less and less pressure and density as you go higher. In reality, there are some complications here. If you've learned about atmospheric physics, you may know that there are a couple of layers due to weird ionization factors and like the ozone layer and things that cause some uneven heating. So really the density is a bit more complicated. But and then I wanted to add this picture here on the left because there's something called vapor pressure that I wanted to mention, and that's not talked very much about in the book, just kind of as an aside, which is this idea that if you have a liquid, so this is a picture of a liquid, boiling, but if you just have a container of a liquid, some of the surface of the liquid will constantly be evaporating and turning into vapor. And the reason for this is that some of the molecules in the liquid will occasionally get enough energy that they can just jump off away from the surface and become a gas. So it's important to remember that, liquids and gases are just different phases of matter that most, substances can be either of them under the right conditions. And so there's always some equilibrium between them, if you think about Le Chatelier's principle type stuff from chemistry. And so even if you have what you would hope would be some empty tube, some vacuum, something like that, if it's sealed with a liquid, like a barometer that we'll see soon, you'll end up with some small pressure in the top due to this vapor. So gases, the takeaway from the slide is that gases will naturally form from a liquid and produce some pressure due to their gaseous nature that's independent of gravity, and that really just depends on their concentration and basically the ideal gas law. So okay, and sorry, I should have mentioned this, but feel free to stop me if you have any questions. I figure this intro stuff is probably pretty basic, but there are lots of little nuggets of wisdom that hopefully sneak their way in, and maybe some of you have questions about some of these things. But anyways, so once you start to think about atmospheric pressure, so the book uses this number 101 kilopascals a lot for one atmosphere of pressure, but in reality, it's much more complicated than that. And there will be a few homework problems, I think, about this idea that due to uneven heating on Earth, so some regions are hotter than others, some regions like where there's snow reflect more light back out, and some areas have higher elevations. Due to all of these complex factors, the pressure and the temperature of the atmosphere around Earth changes a lot. And that's what weather is, right? And so in reality, this 101 kilopascals can range anywhere from like, 85 kilopascals all the way to like 105 kilopascals, give or take. Some of these can be even more extreme if you include like hurricanes and stuff, but maybe that's not a fair thing to include. And so for me personally, this is why I don't really care if you use the 101. I tend to just use 100,000 or 100 kilopascals, because the one, it just changes by the day. And in fact, a really cool thing you can do is if you get on your phone and look at the weather app, if you scroll down, it'll actually tell you the pressure. So right now, my phone says that the pressure is 30.01 inches of mercury. So we live in the US, so we get these gross units, which is a slightly high pressure. And so a higher pressure signifies a colder mass of air, and generally means the weather is going to be pretty decent at the moment. We can also look at how pressure changes over time, and that's a much better predictor of weather. And going back even to the 1800s, people used changes in pressure of the atmosphere to predict the weather over the next couple of days. So if you see the pressure starting to drop, that's telling you that warmer air is coming in, which usually will condense and bring moisture, so you can expect storms. And so these maps that you see on like the Weather Channel nowadays actually show these pressure fronts, so warm air and cold air moving into each other. So for example, you can see that there's this cold front here moving to the right, and that's a region of high pressure. So gases are a little weird. We'll talk more about them next week, but colder gases that aren't in a container will increase their density. And so for that reason, they'll increase their pressure as well. It's a rather tricky relationship, but it's this interplay between pressure fronts that leads to wind. So, you have some region of high temperature, low pressure, that's going to rise up, and it's going to be replaced by a region of higher pressure or lower temperature. And then as that cools, we get these big cycles. And so the whole Earth is generally hotter at the equator, colder at the poles. So we'll get currents of air flowing from the poles to the equator, and then they end up getting twisted due to the rotation of the Earth, known as the Coriolis effect. And so we get these nice spirally patterns that spiral from the poles to the equators and form a bunch of little circle-y cells of wind. So it's a complex and beautiful set of phenomena. What you'll be expected to know for this, though, beyond just some of these facts, is mostly covered. Well, some of the basics are covered this week, which are just understanding pressure and understanding density and how they change. But the more complex aspects we'll do next week when we get into the ideal gas law. Anyways, and like I said, feel free to just raise your hand if you have any questions about this, but I know it's nothing too insane yet. Okay, so I put a pressure gauge here to remind us of a useful idea, which is gauge pressure. And so if you go to the store and buy a tire pressure gauge, and you hold it in front of you in the atmosphere where there is 100,000 PSI of pressure, it'll say 0, right? And that's for a good reason. It's because everything that we're going to use, unless you're an astronaut, is going to happen on the surface of the Earth. And so we don't want it to tell us about the atmospheric pressure. That doesn't really impact many things in everyday life. If I'm filling my car tire with air, I don't need to know what the atmospheric pressure is. I just need to know that I get enough air into the tire. And so this is the idea of gauge pressure, which is just the actual pressure minus 1 atmosphere. Now, gauge pressure is convenient, but it's really annoying as a physicist because every equation we're going to work with cares about the actual pressure. So this is what the equations will use. So you may be given problems in the future where we give you a gauge pressure, because that's what you would actually get if you were in the real world. You know, somebody would tell you a gauge pressure. You have to convert it to an absolute pressure. So this P here, use that in some equation, like maybe the ideal gas law, get your answer, maybe you get a pressure as your answer, and then convert that back to a gauge pressure. You might have to do this whole song and dance in order to accurately capture the physics, because while we don't care about the fact that there's one atmosphere a lot of the time, the molecules of air do feel that. So if you have a container of air, if you have your tire and you fill it up with extra pressure, those air molecules are moving in such a way where they feel not only the force from your inflation of the tire, but also the force from the atmosphere. The gas molecules do understand that there's a bunch of stuff on top of them, even if we can mostly ignore it. Okay, and this is a good time to mention why we can mostly ignore it, which is that, you know, we're not having to deal with vacuums very much. So if we breathe in or breathe out, we're cycling gas that's roughly at 1 atmosphere. And so there's, you know, if I take a container and I pull all the air out of it, the atmosphere can usually easily crush it unless it's a specially made container. So if I, you know, take a, you know, this tea bottle and took all the air out of it, it would get crushed immediately. You'll find lots of videos of this on YouTube. But because everything, you know, is from the surface of Earth and is in some sort of equilibrium with any gases on the inside having the same roughly atmospheric pressure, we don't see this crushing happen very often unless we do some sort of suction. And, you know, you can do this even if you take a straw and just plug one in and suck the air out of it, the straw will get crushed. That's the atmosphere crushing it. So this was a common misconception. Actually, even Galileo thought that there was some force from suction that was crushing things, but it's actually the other way around. This is what Torricelli figured out, why we named the millimeter of mercury after him, is that it's not the vacuum itself that's doing anything, it's the fact that there's an ocean of air pushing against it. So if you did that same straw experiment in space, nothing would happen. It would, because you're not pulling anything out. There was nothing there to begin with. So kind of cool to think about. You know, if you're thinking about anything with the atmosphere, it's always good to check yourself by imagining what would happen if I were in space, you know, in the vacuum. Would it be different? And you'll definitely be given some sort of qualitative problems checking your intuition about this as we go. Good. But, you know, I should mention that as we go, like, let's say you're a scuba diver and you go deeper underwater, now you're having more external pressure than what, so let's say you take a breath of air and you dive down. So not scuba for a moment, just free diving. Now you are being compressed as you dive deeper. And so there are some limitations on human diving due to that. When you scuba dive, you have an incredibly high pressure tank, way higher than any pressure you would experience in normal diving. Like recreational diving can only go down to 100 feet or so. And so that high pressure tank is enough to inflate your chest, even though the outside is a much higher pressure than you're used to. So if you swim down 30 feet under the water, you have an extra atmosphere of pressure, but the air in your tank is enough to still push your chest out as you take a breath. And it does this with a clever mechanism known as a regulator that we can talk more about. Okay, so now is a good time to try a problem. So I'll try to do some problems with you as we go so that you get some practice, but we'll also make sure you have problems in discussion. So in this problem, we have a 10 centimeter diameter suction cup pushed against a smooth ceiling. What is the maximum mass of an object that can be suspended from the suction cup without pulling it off the ceiling? The mass of the suction cup is negligible. So I've included the figure from the book here that shows the free body diagram. But the idea is that when we have this suction cup, we've removed the air out of this region. So I should just say there's nothing in here, but there is air outside of it. And so it's this outside air, even though it's pushing up. I should have mentioned this earlier that, when you have a fluid that some pressure is applied, it's transmitted throughout the object. So the pressure, at 1 atmosphere can be applied in any direction. Pressure is not a vector quantity. It's actually a scalar quantity. So it doesn't have a direction associated with it. It just exerts itself in any way that it can against any surface that's present. So here it's exerting itself upward. And that upward force is what's going to hold. So this is the force from the air, is what's going to hold the suction cup. This is the weight, mg. And you can see in general, there'll be some normal force here as well. But when we're trying to find the maximum mass that the suction cup can hold, we can say that the normal force is going to 0. Okay, so if we have a lighter mass, then in order to balance that force from the air, the ceiling will push down on the suction cup. But right before the suction cup is going to fall, we add more mass, more mass, more mass. The ceiling is having to push less and less hard until eventually the suction cup pops off. Okay, so in order to do this problem, we can just set F air equal to mg. So they're going to balance each other when this is just about to fall. And the force of the air, remember that pressure is force over area. And we know the pressure of 1 atmosphere. So this is the pressure of the atmosphere. We can multiply that by the area of this cup, and that'll give us the force of the air. We set that equal to mg. So the area of this cup is just pi r squared. And the pressure of the atmosphere is 10 to the 5th pascals. And we can divide by g, which is 9.8 meters per second squared. And if we plug this in really quickly. Oh, and I should have mentioned this, but it's in the syllabus. You really do want to have a calculator for this class. It doesn't have to be a fancy one, but it should definitely at least have trig stuff. It doesn't need to be graphing. I'm not going to ban any models of calculators, but you won't be able to use your phone on the final. And it's best to get used to a calculator before you're expected to use it for something high stakes. Okay, so I plug this in and I get about 80 kilograms. Remember to convert your centimeters into meters before you square it. And so this is kind of crazy, 80 kilograms, that's more mass than me. So if I had a small 10 centimeter suction cup, I could stick it on the ceiling and it could hold my entire weight, which is, saying something about the realism of James Bond. But in reality, there are some difficulties with that, right? If that seal is broken at all, if the surface of the ceiling is a little bit rough, it can let little channels of air in, which will pop the seal. The inside will then be at 1 atmosphere of pressure, and then you don't have anything holding you, right? The only way that you can have something like this work is that you keep that region inside the suction cup evacuated. You don't let any air in, which can be hard to do in practice. But if you can do it, you can really have incredible forces. And in fact, industrial equipment in a lot of factories uses suction cups in order to move incredibly heavy pieces of equipment without damaging them. So it's a commonly applied tactic. And suction cups are used in medicine as well, but some of their uses are a bit more esoteric. Okay, so any questions about how we did that problem? Yes. Yeah, so you can imagine if I just put the suction cup to the ceiling and there's no mass hanging from it, the suction cup isn't going to move, right? It's going to sit there, but the force of air is pushing it up. So there has to be some force pushing it down that balances in order for it to not accelerate. That's the normal force. So if I don't put a mass on the suction cup, the air will push it up and the normal force from the ceiling will push it down, and that'll cause it to be balanced. As I add more mass, the weight now is pulling down. So we don't need as much normal force. The normal force will adjust in order to, make something stay still as long as it can. And so the normal force is going to decrease. As I add more weight to the suction cup, it gets pulled down more. And so the normal force, the force the ceiling is pushing down with, decreases until I get to this point that we're trying to calculate, where it's the maximum mass that it can hold. And once we get to there, the normal force now doesn't have to be anything. It's just zero. And then if we add more mass, it'll plop off. So it'll stop being, a realistic. Or we would just have to start thinking about the acceleration and it gets a lot more complicated. Once the seal is broken, basically that force from the air doesn't exist anymore. There's some complicated dynamics in the moment, but very quickly it's just a falling object. Does that help answer your question? Good. Okay, any other questions? Awesome. Okay, so now we're going to talk about fluid pressure. And this is a really fun, sort of relevant topic because of the whole submarine disaster thing. It was in the news a lot lately, how when you go deep below the surface of a fluid, you get incredibly high pressures. And so I want to give you the tools to calculate those pressures. It's very easy, actually, surprisingly easy. So the idea here is that if you have some container, you can think about it as a so-called column of fluid. So what that means is that you see how this is like a column here. So that weight of fluid is pushing down on the bottom surface. That's what's causing the pressure to increase as we go deeper. And so if we have some pressure at the top, let's call it P0, we'll have some bigger pressure P1 at the bottom. Okay, and so it's easier to temporarily think about this in terms of forces. So the force at the bottom, F1, is going to be equal to the force at the top, F0, plus the weight of the fluid, mg. Right, so however hard the atmosphere or a piston or something is pushing on the top surface of the fluid, that's F0. And then we're going to add the weight of the fluid itself, because that's also pushing down. And then we're going to get the force at the bottom. That's F1. And so remember that pressure is a force per area. Now, it's nice when you're doing things with fluids, you might be tempted to use forces, but unless you have to, unless you're being asked about how something is being pushed or accelerated or something, it's usually best to convert these forces into pressures. The natural quantity for how hard a force, for how hard a fluid is moving or pushing on something is a pressure, because of how fluids, contort themselves and they don't really have a direction that they're applying this in. So that's why we like to use pressures. So this is P1 times A. And then the force 0 is P0 times A. You can see that the reason we think about these columns of water is because they have a constant area A, this circle. This is our area A, and it's the same up here. And then for the mass, it's nice to see that the mass we can represent in terms of the density. So mass is density times volume. Okay, the density of that fluid for water, remember, it's 1,000 kilograms per cubic meter times the volume of this column. But the volume of a cone or a column is A times H, that cross-sectional area A times the height of the column H. So we can replace the mass with rho AH. We still have the G here. And now we can do a little simplifying. We can cancel all these A's. And we get that the pressure at the bottom of this bit of water is equal to the pressure at the top plus rho GH. I'm just going to rearrange those letters because of the way we usually write it. So rho GH is the important thing here. So hopefully this is kind of intuitive once you look at it a little bit. The idea is that what determines the pressure below the surface of a fluid? Well, it's determined by what planet you're on. You know, so on Earth, that G is 9.8. If you're on the moon, it's 1/6 as big. So an ocean on the moon, the pressure would increase, you know, 1/6 as fast. It's dependent on how deep you are. So the deeper you go, the higher the pressure will be. And it's dependent on the density of the fluid. So if you're under salt water, it's slightly denser than fresh water. So you'll have a slightly bigger pressure. Or if you're under mercury, you'll have a much bigger pressure, 13 times bigger, or 14 times bigger. So this formula is really critical for a lot of the problems that we'll do. So anytime you're dealing with a fluid under the influence of gravity and you're interested in the pressure at some depth, we can just quickly use this equation and figure out what the pressure will be. And so to give you an example of this, here's a picture of the ocean, again, from the fact that there was a recent submarine disaster. A lot of these are easily available online. And there are a couple of cool things just to point out here. So the first thing is, you know, we think of sperm whales as going really deep, but they actually only go around 1,000 meters. The meters are listed on the right side here. The Titanic wreck is almost at 4,000 meters. So we could take that height as roughly 4,000 meters. And so what we can do is we can quickly use the pressure. So let's just calculate the difference in pressure. So how much pressure is due to, this is P1 minus P0, how much pressure is due to the water. That's just the rho GH component. So for water, rho is 1,000 kilograms per cubic meter. And then we know G is about 10. And then the H here is 4,000. So putting this all together, we have what, 40 million? Pascals. And remember, what is one atmosphere? Can anyone tell me? Figures? An atmosphere? Yeah, 10 to the 5, 100,000 pascals. So how many atmospheres is this roughly? 400 atmospheres. So if you think one atmosphere is a crazy amount of pressure, imagine 400. Okay, this is really just crazy amounts. And in order to build something that can go that deep, it basically needs to be a sphere, so that the pressure that's being applied is applied evenly in all directions. So as long as that sphere is strong enough, usually it's made of metal, like some steel alloy or titanium even, it'll be compressed uniformly and it'll hold its shape because pressure is being applied from all directions. Now, the deepest point in the ocean is almost 11,000 meters. And you can see that because this equation is linear, right, doubling the height doubles the pressure, we can immediately, guesstimate that. So that's about 3 times deeper. So that would be about 1,200 atmospheres if we went to the bottom of the Challenger Deep Marianas Trench point. The fun thing to point out here is that if you build something to go into outer space, it only has to handle a 1 atmosphere pressure difference, right? There's 1 atmosphere inside, 0 outside. If you build something to go to the bottom of the ocean, you have 1 atmosphere inside, 1,000 atmospheres outside if it's at the bottom of a trench. The Navy submarines only go to around 3,000 or 4,000 meters. But anyways, so they have to, you have hundreds to 1,000 atmospheres of pressure difference. So much, much harder to build something to go in the ocean than to go in into space. And this is a good time to mention actually as well that 10 meters of water is roughly 1 atmosphere. So if you do the calculation with rho GH, you'll find that to get 1 atmosphere, you only need to go 10 meters. So every time you go out snorkeling or something, you can easily go down and get an extra atmosphere of pressure onto your body. So you would have 1 atmosphere from the air and then 1 atmosphere from the water for a total of 2 atmospheres. But remember, your gauge pressure, if you had a gauge with you, would just show 1 because we ignore the air's atmosphere for gauge pressure. Okay, any questions about this example? Yeah.
For example, I just wanted to ask, what was F0?
F0 is some force applied at the top in a downward direction. So, the reason we include that is because the atmosphere, air, would be something that would exhibit that sort of force. So, the weight of the air is pushing you downward, so there would be some force on the top of the container, F0, and it's spread out over an area A, so we think of it as a pressure. Very good to clarify. Okay, so this brings us to a couple of interesting situations. So one situation that is probably just pretty intuitive, but is kind of cool, is that if we fill up some weird shaped container with water, that no matter how the shape of the container is oriented, we'll always get water coming up to the same level in some connected container. So I think this is one of those things that it's like the more, there's kind of a Dunning-Krugerish thing, the more physics you learn, the weirder this sounds until you kind of understand it, and then it's like reasonable again. So I think with no physics education, this is probably what most people would guess, is that if you fill up a container, no matter what the shape, with water, all the different levels will be the same height. But when you start thinking about these columns of water, like we used in the last problem, that starts to feel kind of weird because, for example, like this point doesn't have a column of water above it, right? It's just has a closed pipe above it. So why is it that the pressure here is the same as the pressure over here, where there is a column of water above the point? It comes down to something known as Pascal's principle. So Pascal's. Which is the fact that fluid, where a pressure is being applied, transmits that pressure throughout any interconnected set of fluid. So basically, any pressure applied here is going to be pushing sort of outward in all directions. And so even if you're down here, you've basically been pushed on by all of the adjacent water molecules. And for calculational purposes, we can treat this rather simply. So if we wanted to find the pressure at the top of this closed pipe that's completely filled with water, we would just think of it as being at the same pressure as a point at a similar height with water above it. So we would just do our rho GH to get the pressure here, or the gauge pressure, I should say. And so we would use, since this is 100 and this is 40, this is 60 centimeters. So to get the, well, let's call it the gauge pressure, which is just rho GH, we would again do the density of water, which is 1,000, G, which is 9.8, but we could say it's roughly 10. And then our height is 0.6 meters. And so the pressure here would be 6,000 Pascal, which sounds like a lot, but an atmosphere is 100,000 Pascal. So what this should tell you is that normal heights of water don't change the pressure by crazy amounts. You really need 10 meters, right, to get something that's an atmosphere. But I think this is something that starts to trip people up. So hopefully this idea makes sense that we can, for a closed container completely filled with water that's connected, like the water can feel adjacent molecules. In order to get the pressure at any point, we just measure from the surface level of the water down to that point. That's our height for rho GH. And then we can just use the formula. So there's not too much work to do here, just understanding how fluids transmit pressure. Yes.
Why don't you use 67, not 47?
Yes, because we want to measure how far is that point from the top of the liquid, because that's the height, you can imagine it as the weight above that point, right? So that's the weight above that point, and it's being transmitted through all these water molecules down and around. And so, the pressure at this point is due to that whole 100 centimeters of height. But as we go back up, there's less and less water on top of us. So we only end up feeling the weight of that 60 that's above us. Even though it's not directly above us, the fluid's connected, so it transmits the pressure. Good. Now this is a very good question. So I appreciate everyone who's taking the time to ask. Okay, so this leads to an important set of consequences. So that so-called Pascal's principle. And if you go to any construction site nowadays, you'll see the direct result of this idea, which is hydraulics. So anytime you have hydraulics, they're basically working on this mechanism, this Pascal principle mechanism. And so the way hydraulics work, at first it sounds impossible, but I'll show you why it's allowed. So let's say that this maybe is 1 square centimeter, and this is 100 square centimeters. And that this entire blue region is filled with fluid. So it could be water. In a real hydraulic system, it's a kind of oily fluid called hydraulic fluid. So what happens is that any pressure applied up here gets transmitted through the whole fluid. And so if we ignore the differences in height for a moment, so just imagine the system were horizontal, or that it's so short that the rho GH terms don't really matter. So ignore rho GH for now. Then whatever pressure we apply up here would be the same pressure that we would see over here, right? Ignoring the pressure due to the height. So now we're generating pressure in the fluid by pushing on it, which is another equally valid way to pressurize something. And so what this means, remember that pressure is a force per area. So if we want the pressures to be the same, if the areas are different by a factor of 100, so if we call this A and this B, so FA over AA, okay, that's some bad notation, is FB over AB. So if this area AB is 100 times bigger, that means that the force FB also has to be 100 times bigger, right? So if let's say we applied 10 newtons, so we put a 1 kilogram mass up here over 1 square centimeter, in order for this to be balanced, we would have 1,000 newtons or 100 kilograms on surface B. So if we wanted to balance these two surfaces, if we wanted them to be in equilibrium, we put 2 pounds on the left side, we can put 200 pounds on the right side, and they would balance. Isn't that crazy? Okay, so this is the power of Pascal's principle, is that we can lift incredibly heavy things, but it's the same idea as like a lever or a pulley. It's really another type of simple machine. If it had been understood earlier, we would probably call this a simple machine. So, with a lever, you can imagine seesawing with someone. A little kid can lift their parent if the little kid slides to the end of the lever and has more torque, right? So it's a really similar idea here, that a small mass can lift a much bigger mass, so long as it is acting on the smaller area, and therefore has to move a larger distance if we want this system to equilibralize. So if I move this down by 10 centimeters, then we can imagine the area here, or sorry, the volume of fluid in this region. So this volume of fluid has to flow to this side to increase it. And so this will only move up by, maybe half a centimeter or so. Right, so the way that this isn't like just a broken bit of physics, and the way that it's a little bit, not as good as it sounds at first, is that in order to move, if we wanted to lift the heavy thing, we have to move the little side a really far distance to move the big side a little bit. And so what that tells us is that the work we're doing on side A is the same as the work we're doing on side B, right? That whatever force we're applying here times the distance we apply it over has to equal the force we apply here times the distance we apply it over. And so, that distance idea just comes from the fact that the volume of fluid leaving the left side is the same volume of fluid that's filling the right side. And there's a clever bit of engineering that you can do to make this less of a problem, which is used in any hydraulic jack. So you probably have one shoved somewhere in the back of your car right now. It's a good idea to know where it is in case you need to change your tire. But so we have the big side where the car is sitting, that's this high pressure oil. And we have the little side, which is where you pump up and down. And the up and down motion allows fluid to flow from an unpressurized tank into the pressurized system, so that instead of just pushing down forever to lift the car, we can push up and down, pull this fluid from the tank into the system, so that that volume can be pressurized by you and push into that larger cylinder that lifts the car. Okay, so maybe that explanation wasn't amazing, but basically we don't want to have to push this down forever, because eventually we would have to build a hugely tall tube in order to do that. So just a nice engineering trick is to have this so-called reservoir of low pressure oil that has some one-way valves, so it can only flow one direction, that flows into the system. And then when we push down on the handle of the jack, that oil becomes pressurized and is able to move into this larger pressurized enclosure and lift the car. So kind of clever, and you probably all have one if you have a car, or at least know someone who does. Okay, so now we should move into this idea of a barometer. So a barometer is the original method of pressure measurement. It's not as common anymore, but it's still the most accurate way to measure pressure in a certain, unless you're trying to measure really, really low pressures. And so the way you make a barometer, you can do it at home. It's pretty easy. So if you, it's just that it won't work too well at home for a reason we'll talk about. But you take some fluid and you fill like a cup. So you take a normal cup, you fill it up with water, you close the bottom, you invert it, and then you put it into a dish also filled with some fluid. So that same fluid. And so what will happen is, you can imagine if that dish weren't there, the fluid would all just flow out the bottom. Okay. And so when the fluid flows out the bottom, it would want to, naturally it would want to lower in height. So that region was originally all full, and then some of it would flow out, it would lower. But what we can do is by submerging it in a dish, the atmospheric pressure is able to nicely push on the system without. So the reason it doesn't work if you just have a column is that small fluid flow instabilities and surface tension can really mess up the system. So in a perfect world, you could just have the column part and it would work as a barometer. You wouldn't need a dish. But there are a bunch of little complicated microphysics details that make it much easier if you have a dish for the water to sit in. So anyways, then this fluid wants to pull down. It has some force mg pulling it down, but because of the atmospheric pressure on the surface of the fluid, there's a similar pressure pushing it back up. Right, this is one atmosphere of pressure pushing it back up. And so what we can say is that the height for the height of this fluid, rho GH, this equals, in this case, 1 atmosphere. So whatever we're exposing that barometer to. So if it's sitting in the room, that would be 1 atmosphere. And so by measuring the height of the fluid H, we can figure out what the pressure is, right? If we know rho of the fluid and we know G, then this will tell us an exact value for what the pressure is, and maybe pascals. And so a shortcut people do, like I mentioned earlier when I was telling you about the weather app on my phone, is that they'll make this system out of mercury, and they'll actually just tell you what this height is and use that as a unit of pressure, because that height itself is directly proportional to the pressure on the system. Okay, so we can imagine if there's more weight pushing down on this water, it'll squeeze it up the tube and that height will increase. So as, let's say, a cold front comes in, the pressure of the atmosphere increases, more pressure is pushing on the surface, more liquids pushed up the tube, and we get, more inches of mercury or whatever it may be. Now, the reason that I keep referring to mercury is because it has a really high density. And you might say, well, what if I just want to use water? I have lots of water, I can do this. Well, think back to our ocean example. How much water height does it take to get 1 atmosphere? It takes 10 meters, right? So like 33-ish feet of water to get 1 atmosphere of pressure. That's a really tall tube. So that's why you can't really easily do this at home. You would need something, 3 or 4 story tall tube in order to make this work properly. And additionally, water has a high vapor pressure. So if you have a glass of water, if you set it in your room and don't clean up after yourself, you'll notice that the level slowly decreases over time. That's the water just evaporating into the atmosphere. And so that vapor from the water exerts a pressure once it's in a gaseous form. So if you have water in here, this top area would have some water vapor, and so it wouldn't be a true vacuum. And we would need to know what that pressure is in order to accurately calibrate the barometer. So that might be a question you're given on the homework, so look out for that. But anyways, so with water, we need 10 meters. Mercury is 13.6 times heavier, or times denser, I should say, than water. So we only need, let's see, 10 divided by 13.6. We only need 73 centimeters of mercury, which is much more manageable, right? So you need something like this tall, and you can measure atmospheric pressure with mercury. So you can have that in your house. Anyways, so yeah, barometers really important. And the principle behind them is basically just this rho GH equation. Any questions about this while we're here? Okay. And so actually this leads to a fun result, which is that when you drink something with a straw, what you're doing is you're removing the air, you're creating a vacuum at the top of the straw. So it's sort of like a barometer. And so the pressure of the atmosphere on the surface of the liquid is pushing it up the straw, right? A vacuum doesn't create a force, it just allows other forces to act. And so if you have a straw of a large diameter, then you can actually only drink at a height up to 10 meters, because the pressure of the atmosphere isn't strong enough to push the water any higher than that. The weight of the water in the tube is too much. Now, practically speaking, you can only do maybe 1 meter from a straw. You can try it at home if you've got some plastic tubing. If it's a large diameter, but if it's a small diameter, you can actually drink much, much higher than that. So you could actually, if you have a small enough diameter straw, you could drink from 100 meters high. And that is due to capillary action, which we're going to learn about. So I know you've maybe heard about it and it's like some mysterious thing. It may still be mysterious after the class, but you'll at least know some equations on how to calculate things to do with it. So anyways, this straws are very similar to these old style, they're called siphon pumps, where this upper piston creates a vacuum at the top of the pump that pulls water up. And so that can only pull water up a height up to 10 meters. And realistically, only if it depends on how good the vacuum is, only 5 or 6 meters. But you can pump water from a deeper well. You just have to do what's called force pumping, where you pump air down because now you're applying a pressure. You're not relying on a vacuum. You push air down into the well, and then that pushes the water up. So always think critically when there's forces or suction involved. With suction, you're relying on the atmosphere. So you can only exert that much force. But if you're actually pushing air or water with a pump or something, and this is why submersible pumps are so nice and common, you actually put the pump in the water and then it can just grab it and push it somewhere. Then you can do whatever you'd like. You can have a submersible pump push with arbitrary force. Okay, and so there's a nice example here from the book, which is if you have some oil and water in a tube, the oil is going to float on the water due to its lower density. And so a good question is, how does it orient itself? So oil has a lower density. So does anyone want to take a stab at which picture accurately represents the situation? Yeah. C? Yeah, it's C, correct. So remember this rho GH, the rho depends on the fluid. So here, the rho is lower. And so we need more height in order to get the same pressure, right? The pressure at the bottom has to be some number. So it has to be the same from this side as from this side. If it were different, then the fluid would flow in that direction until it came to equilibrium. So option C is correct. Okay, we're almost out of time for today. I guess I'll get into buoyancy in the last 2 minutes, but we'll start back here tomorrow. So I want you to think about this weird fact. Cruise ships, they can literally be like the size of, huge hotels or even bigger, but they're able to float. Whereas if I take a little tiny pebble and drop it in the water, it'll sink. Okay, so, insanely large, thousands of tons cruise ship floats, tiny little pebble sinks. It's weird, right? So what determines if something floats or sinks? It's not its mass, it's its density. And that's why we talk about density so much, is that it's a material property that's really relevant to fluid dynamics. And so for some object in fluid, there's more pressure coming from the bottom than there is coming from the top, because the lower down you are, right, you have this weight of the water pushing down, and then that gets transmitted throughout the fluid and pushes you back up. So the bottom of an object is getting pushed up. The top of the object is getting pushed down, but with a smaller force. So that creates some buoyant force. And even if something sinks, it still has a buoyant force being exerted on it. So if you go into a pool and you breathe out the air in your lungs so that you sink, you'll still feel kind of, light, right? You feel kind of like you're on the moon or something. You can bounce around on the bottom. And that's because there's a buoyant force pushing upward due to this pressure gradient from the rho GH of the water. And that's countering your mass, which is wanting to pull you down. And so you can easily show this for a cylinder, which we'll do next week. And then it turns out to be true for any shaped object due to some clever arguments. But it's 9:20, so I'll leave it here.